Hello. Today we have a quick little lesson on definite intervals as summation notation. So this is a tested topic. Mostly you'll see it on the multiple choice section. So we'll do some practice here. We're going to develop the concept up here so you can understand the notation. Then we'll do a real quick practice on a couple at the bottom, and that will be our lesson for today. So basically what we're looking at here is finding the area under the curve using a combination of summation notation and applying that to the definite interval that we've been looking at. So as we do this, we're going to kind of tie back to a couple of things we've talked about, Riemann sum, and how we can use that. So the first thing is we're going to estimate the area under this curve on the interval from -1 to 6. So that means we're going to be approximating the area from -1 through 6 right here. And so if we're finding the area under the curve of that right here. So we can see we've got some positive areas, we've got some negative areas. Using this notation that we're going to build here on this problem, then we're going to be able to not have to worry so much about subtracting off that negative area. It's going to become part of the problem. Okay, so it says we're using right Riemann sum. So you should definitely know that this is for right Riemann sum, not left Riemann sum. So we're going to kind of go back to a few things that we know. For instance, we know that if we're using 7 subintervals, then how wide is each triangle? Do you remember from previous lessons how we could find the width of a triangle in interval notation in Riemann sum? Well, hopefully you remember something called delta x, right? And then that delta x was b minus a over n. So the upper bound minus the lower bound over the number of rectangles. And so if we apply that to this particular problem, then delta x is going to be b minus a -1. Oh, sorry. B is 6. So 6 minus a -1 over, and it said the number of intervals we're using is 7. So what does that tell us? That tells us that that width in our Riemann sum is going to be 1. Okay, so that is this first part, how wide. So if using the subintervals, how wide is each rectangle? So that means I need to find the width of any of the rectangles that I might use here. So then using this same concept from A, the only difference is now my delta x is going to be b minus a over n subintervals. So in any case, that's how you would find it, right? The difference is we don't know the number of subintervals. So if we're asked to find n subintervals, we would use an n, which translates to this problem being 6 plus 1 over n, or 7n. Okay, and so that's what my delta x would be in terms of this particular interval. Excuse me. And then C, to find the exact area under the curve on the interval -1 to 6, we need infinitely many rectangles. Because if a width of 1 is going to give us a good approximation, if there were 100 rectangles between here, little bitty slivers that we get closer and closer each time to that curve, then that's going to make a much better approximation. So as n approaches infinity, as the number of intervals approach infinity, what is happening to the width of each of those subintervals? Well, hopefully you can see then that they would be approaching 0. So we can say delta x is approaching 0 because each rectangle width is not going to get to 0, but it's going to keep getting smaller and smaller and smaller, moving in that decreasing distance. So as we get infinitely many, the widths of them get infinitely small. And the more rectangles that we have, the closer our area approximation is. Okay, so now let's kind of look at applying some of that to how we would go about this process. So if we look at each of these widths and we said our width was 1, so that means this width right here is 1, then we need to know the height to get us up here, and then we can accumulate those things. All right, so let's just say if I started from here to here, and I wanted to move from one triangle to the next, that means I'm changing my function value. So hopefully you can see that we would start at our first function value, which is -1, and then we would add the increment, which is however much this distance is to get us to the next value. So that would be the width of the rectangle. So that's going to be 6 plus 1 over 7. And that would get me to here. Okay. So what if I wanted to go from the -1 originally all the way over to 1? Well, then I'm going to say I'm still going to start at 1, and I'm still going to have an increment because all those widths are going to be the same. But how many am I going to have? I'm going to have to go over 1 2 times to get to right here. So then I'm going to multiply that by 2, which means technically, if you want to get mathematical about it, that could see the same as multiplying the width by 1. Okay, so let's do it one more time. Let's go from -1 over 3 times over here. So we're still going to start with a function value -1 because that's where we're beginning. We're still going to have to add our triangle width to it. But how many times are we going to do that? We're going to add it once to get to here, once to get to here, and one more time to get to here. So we're going to take that width times 3. Okay, so that's what we're building our function value. So generalizing this into a formula, to get the height of each triangle, we're going to take our function value. And what was this? Where did we start our interval at? We started it down here at -1. So that's going to be my A plus, and then the width of my rectangle was calculated by doing B minus A over N. And then this is the number of times that we are adding the increment to it, or in this model, we call that K. And so that's how I get the height of my triangle. Excuse me, the height of my rectangle. Okay, so now that we've done this with numbers, we calculated here the width of each rectangle. That's that distance from here to here. And then we said to get the height, which is the distance this way, then we're going to take our beginning bound and we're going to add increments to it to get through the curve. Okay, and so the increments are going to be B minus A over N, or that's that delta X. And then K will be the number of increments. So the number of times you're going to increase it to go from triangle to triangle. And then, so let's go ahead and identify real quick here. A is the lower bound. And why is there an F on the outside? Well, because the height is the function value or the Y value of your rectangle. Okay, so now that we've kind of built some of the concepts here that we're going to use, we're going to go down here to this actual area under the curve. Keep in mind we're using kind of a form of right Riemann sum. So again, right Riemann sum, that's how we get the triangles here. And then remember that anytime you are finding the area of a rectangle, it's base times height, or width times height. So we're going to keep that in mind as well. Okay, so as we build this model, we are looking at the limit as n approaches infinity. So remember, limit symbol LAM, n approaches infinity. So that's where we're talking about making an infinite number of rectangles so that it's going to get smaller and smaller and smaller, so that we're adding up smaller and smaller values. So imagine taking this one width and drawing 10 lines in here. Okay, that's going to fit this curve a lot closer and make each triangle smaller value. So we're adding up smaller values to get there. Okay, so we have, as with any limit notation, a lower bound of 1. That's the first rectangle we're going to calculate, to some inbound. All right, so base times height. So we just found the base, or the width of the rectangle, would be B minus A over N, and that's my delta X, or my width. And then the height is the H value, or the function value. So we're going to have F we're going to begin with the lower bound plus, and then we're going to have the width. This is the increment. So the width times the number of increments. So that K just means how many times we're going to do that. How many of these are we going to create? And so this is the height. So there's your base times the height. And because we are definitely talking about definite integrals, then that all of this limit as K of 1 to N sigma, and this part of it equals basically the summation from A to B of f of x dx. So this is the calculus symbol that represents what we're doing right here, which is accumulating and summing up the area in really small delta x's to using the height. All right, so we're going to work through a couple of problems here. Make sure you got it. It's almost easier to have the whole thing written out and go backwards than starting here, but it's a really good place to start. All right, so example 1, part A. So we're going to be looking at this integral from -3 to 3. We have a function x squared, and we have our dx, all the pieces that are required when we're working with these models. All right, so as we're working through this, then I kind of, I don't know, I think it's easiest to just start by finding delta x. So that's usually where I start this. And so one other thing is, as we're going from n to infinity, we don't know the number of rectangles that we're going to have. So we are going to see these n values in our model because we don't know the number that we're going to break that into just yet. Okay, so the first thing that I do, and I'm going to go ahead and write like my steps down over here, how I'm doing this. Some of it isn't something you would necessarily be writing down, but since we're learning how to do this and working in our notes, then that's where I would start. So the first thing I would do would be to identify my delta x. So how am I going to go about doing that? Well, I know that my lower bound, or A, equals -3. My upper bound, or B, equals 3. And what is the delta x? How do we represent that? That's B minus A over N. So now I'm going to find my delta x for this problem. So I'm going to say delta x equals, and my b is 3 minus a -3 all over n. So that's going to give me 6n. So I have found my width. So that's the first thing that I'm going to do. And the second thing is I'm going to find my height. So that's that f of, we start with our lower bound, plus the delta x. Okay. All right, so we're finding that function value. Well, we've already found delta x. We found that right here. So as I move to figuring out what this is, then I'm going to have f of, and if I look at this integral, then what is my beginning bound? So it's going to be -3, good, plus, and then what is my delta x? That's going to be 6 over n, and then we have to multiply that by k. So you can either multiply it back here, or you can put it on top to get the height. And so now the last thing we have to do is write the model. Okay, so go to the model. So then we are going to have everything goes into the model. So we're finding the integral from a to b. So that's from -3 to 3 of x squared dx is going to equal, we have our limit notation, n's approaching infinity, of sigma notation, where n equals 1 to whatever our n is going to be. And then our height is 6 over n. I'm sorry, our width is 6 over n, and our height is f of -3 plus 6k over n. And so as you're working through that, then that's going to look like this statement right here when you work through that problem. So the last thing we need to do is figure out how this ties back to this model, because you can see that we have this x squared right here. And so I just kind of wrote this statement down so we could start thinking in terms of putting this together as an area. But we're actually writing the definite integral. So we're needing to write this using this to get us there. So our final step here then is going to be to put this all together. So I have on this problem, notice that it is x squared, right? So I'm going to have, let's write our notation, the limit as n approaches infinity of the summation n equals 1 to n. And then we have in our problem, we have the width, which is 6 over n. But then we have to address this right here. Remember, this was delta x, so that's taken care of, but we have to address the x squared. So basically what we're doing is putting this piece right here into our x squared, because this is f of x and this is x squared. So then I'm going to have in my notation the negative 3 plus 6k over n, and I'm going to square it. So taking this is the width, which is dx, and this has to go into my model to actually get my equation. So this is what it's finally going to look like. Okay, so I broke that down into lots of little steps to kind of help you work your way through it. But ideally, you find b minus a, you find the height, and then you go to this model right here. I just wanted you to understand how we were getting through how this was going to tie to this by using what we know about that x squared. Okay, so go ahead and pause your video, and I want you to try b, and then we'll come back and compare. Okay, so let's see how you did. So up here you would have said b minus a is 3. So that means your delta x is 3 over n. And then you would have found your function value. So the a bound is 2 plus the delta xk. So that's your part there. And because this is a function, a rational function, 1 over x, then this looks like 1 over x because we just found our x to be right here. So that's 2 plus 3k over 7. All right, hope you did well on that one. So go ahead and pause your video one last time and work through part C, and then we'll talk about how we're going to work backwards on example 2, which is really, really short and quick. So go ahead and do C. Pause your video now. Okay, so let's see how you did. The limit as n approaches infinity. So first off, I found my b minus a, which is 7. So delta x would be 7 over n. Then my function value is the lower bound, which is 0. So I went ahead and wrote it in my notes, 0 plus 7k over n. But obviously, 0 plus anything is just the anything. So you didn't have to have a 0 here. You could just said function value is 7k over n. So then the limit as n approaches infinity of n over, or excuse me, from the lower bound of 1 sigma to n, then we would have delta x, which is 7 over n, and then underneath the square root, because this is a square root function right here, you would have your 7k over n. Okay, so last little thing we're going to do here, and then we will be finished with the lesson, is we are going to work backwards to figure out what the definite integral was. So notice this time we had a definite integral. This time we have the sigma notation, and we want to write it back into an integral notation here. So a couple of things we need to know. Obviously, we need to be able to find our bounds. So to do that, we look at the model. So we know that when we're looking at this notation right here, that I should be able to find that a value, or the result of the b minus a, excuse me, right there. So I can know starting out in this problem that b minus a equals 5. Where in this formula can I look to see what a is? Right here in this first piece. Great. So now I know what a is. So for me in this problem then, a equals negative 3. And so if a equals negative 3, what's b? So that makes this a negative 3, and then it equals 5. So b has to be 2. So then as I write this, I hope I can see the function itself, which is right here. So I know I'm going back into a square root function. This would be my function value underneath. So then my integral is going to go from a lower bound of negative 3 to an upper bound of 2. And then I'm going to have the square root of x dx. And don't forget the dx, because that's that variable that we have to have when we find our antiderivative. Okay, pause your video one last time. You go through problem B just like I did. Identify what your B minus A is, identify what A is, figure out the function, and then write your integral. So pause your video one last time. Okay, let's see how you did. So notice that this time the B delta X was at the back. This is a multiplication problem, and we know multiplication is commutative, so it could be at the front in front of the cosine term, or it could be in the back. So the top is what my B minus A is, which is pi. Notice there's no plus in front of cosine, so that tells me that A is 0. So then B minus 0 equals pi only when pi is B. So that gives us our bound, and then we can see the cosine term right there. So that's cosine x dx. So I know we've been practicing, using different variables for different things. So just make sure when you use your variable here, it matches up with the integration that you're doing back here. So if this is x, this has to be dx. If this is theta, this should be d theta. Okay, so that is definite integrals as summation notation. It is a not super highly tested piece, but if you can get comfortable with this and you remember how to find your height and your width, it can be an easy multiple choice question to grab and answer correctly on your AP exam. Thanks, guys. See you next time. Bye.